talk of this morning, and I think there will be a photograph. Yeah, when this talk finishes. So please don't run after this. After this talk, and I'm very happy to introduce Soledad Villar from John Hopkins University. She will talk about the exact and appropriate symmetries in machine learning. If someone wants to ask a question, you could come. And is it okay if we interrupt you, Soledad? If
yes, of course. Yeah, thank you.
Thank you.
Yeah. So I'm going to talk about the use of pure mathematics tools into the design of machine learning models. So it's like a different kind of vibe from the things that we were hearing yesterday and today. But I think it could connect very well with some of the things that were discussed. So I'm an applied mathematician working at Johns Hopkins, and I'm going to talk about these exact and approximate symmetries in machine learning models. So as a motivation, you can see that, well, there have been a lot of models that have achieved the state of the art in different domains, starting in 2012 from AlexNet being able to surpass the state of the art in image classification, then these reinforcement learn-based systems that were able to beat the best Go players in the world. And then a few years ago, there was a breakthrough in protein folding using machine learning models that predicted how certain proteins can fold. And last year, we saw ChatGPT and transformers and what things they could do. And one of the features that all these models have is that they are very overparameterized. So they typically have more parameters than data points. And if you're familiar with like the classical statistical setting where one studies a bias variance trade-off, one would expect that overparameterized models do overfit, so cannot generalize well outside their training set because they fit the data very well. And then what happens outside the training set is kind of like overfitting. And there is an explanation of why these models can be overparameterized and also generalized well. That had to do with the implicit regularization. And there's a paper in 2019 by Bacon and collaborators that studied this double descent phenomenon and give some explanations. Subsequent papers give some explanations of this implicit regularization that tells you that, well, the design of your hypothesis class of functions is very important. And sometimes you design a class of functions that overfits when it's overparameterized. But sometimes you can define a class of functions that has the correct inductive bias, and then it generalizes well when you do like your local optimization, you converge to a solution, and the solution not only fits your training data perfectly, but also generalizes well. And this is not very well understood. There's a lot of mathematical questions that have to do with like why this happens and for what kind of models this kind of happens. And there's some heuristics that people use in the design of these machine learning models that seem to have a good property, like this so-called inductive bias. And if you see all of these models that people use symmetries in one form or another. So for instance, convolutional neural networks are designed to exploit image spatial translation symmetries. Recurrent neural networks are designed to be time translation or like have some form of time translation symmetries. Graph neural networks are specifically designed to have an exact symmetry that has to do with permutation on graphs. So they are equivariant with respect to node permutations. And transformers, if you don't consider the position encoder, they are designed to be permutation equivariant as well. So there's like the use of symmetries is something that people have been doing heuristically into the machine learning models. And there's also other reasons why people do it, specifically in AI for science. I'm going to talk about that next. But basically, The idea is that one wants to exploit the structure of the problem and also the structure of the data, and that imposing the symmetries is a very natural way to do it. And this is related with the geometric deep learning literature, where they design what they say how one can exploit the structure of specific problems. And in particular, if we want to use machine learning for the physical sciences, like for instance, the protein folding problem is done using transformers that satisfy translation and rotation symmetries, it makes sense to impose the structure of the problems. And in physics, one can consider two types of symmetries: the active symmetries that have to do with the fact that the physics has some observed regularities, and these symmetries are in a one-to-one correspondence with conservation laws due to the Noether theorem. So, for instance, conservation of energy is in one-to-one correspondence with the time translation symmetry in a dynamical system. Conservation of momentum is in correspondence with translation symmetries and so on. But also there's like a much bigger space of symmetries, which are known in physics as the passive symmetries. They have to do with the fact that when I have a physical object and I represent it mathematically, that representation is not unique. So if I change the representation of my object, then the predictions should change accordingly. And that has to do with the fact that I want to learn a way to learn my physics that is coordinate free, that is independent of the units, that is gauge invariant, and so on. And this also applies to AI for math. And in talks that we had yesterday, for instance, Carlos' talk, he talked about learning some function on lattices, and this function had to be translation invariant. And Radmila talked about these invariants that appear in no theory, and she talked also about this equivariant mapper. And these notions of like being independent of the mathematical representation of an object is very common. And it will, like, if one wants to write a machine learning model that is useful for learning math and math proofs, then encoding the symmetries and encoding the invariances of our problem is something that will be useful in the end. That's what I want to claim. And for instance, I will have an example which has to do with graph learning, which was mentioned in the previous talk, and also it's related with Melen's talk and Ron's talk tomorrow. That has to do with the fact that when we're learning a function in a graph, we can represent this graph as an object with nodes and node features. That here are the colors and edges. And when I represent this object as this graph, when I write this as an adjacency matrix, the representation is not unique. So I can write it as this adjacency matrix, or a permutation of rows and columns will give me another adjacency matrix. And whatever thing that I want to learn, for instance, the shortest path that visits every node starting from this purple one, or I don't know, the length of the path, or what is the path, these questions are agnostic with respect to the representation of the matrix. So they should be equivariant or invariant with respect to this ambiguity in the representation, which here can be seen as the action of permutations on graphs, which permutes rows and columns of the adjacency matrix and permutes the node features. And so mathematically, you can write as like whatever function you want to learn is going to be invariant or equivariant with respect to a group action. So here, for example, I say, well, in this simple example, I have a group where I have rotations by 90 degrees and multiples of 90 degrees. And then this function is invariant if I apply any group element to my input and the function doesn't change. Or it's equivariant if I apply group element to my input and the prediction is also transformed by the same group element, maybe in a different representation, but we can write it as like this commutative diagram. If I apply a transformation to my input and then I do the prediction, it's the same as doing the prediction, then transform the output. For example, in this dynamical system, I want to predict where these points are going to be after a certain amount of time, and this is a system that is equivariant with respect to rotation. So if I rotate all my positions and velocities, then the prediction should rotate accordingly. And in equivariant machine learning, all functions, like the way people do it is by parameterizing the space of functions so that for every choice of parameters, the resulting function satisfies the symmetries. So basically, you just parameterize the functions to satisfy the symmetries, and then you do the learning in this space. And there are other ways to do it, but that's the most common way. And so, yeah, this is an example, for instance, where the action in the input space is different from the action in the output space, because typically in graph learning, one learns an embedding for each node in Euclidean space. So the action here is just action by permutations, and the action here is action by conjugation on the adjacency matrix and permutation on the node features. So how are symmetries implemented in practice? So, well, there's many ways. Some ways are approximate. So, for instance, this data augmentation, loss function penalties, and some are exact, using representation theory, group convolutions, weight sharing, invariant theory, and canonicalization. And I'm just gonna tell you what are the basic tools that people use or like some examples of tools that people use in these three types of implementation of machine learning models that satisfy symmetries. And I think that there are many open problems that are, for people like you, there are pure mathematicians of things that can be done in this space as well. So let's start discussing how people use representation theory for implementing machine learning models that are symmetric with respect to a group action. So, and this is based on papers by Condor, Maron, and there's many papers in this space. I have some references later. If you're familiar with like the classical feed-forward neural networks, basically what they do is they are written as compositions of linear layers with nonlinear activation functions. So you have your input, you apply a linear layer, you apply a nonlinear pointwise activation function like a ReLU, another linear layer, etc. And this is how you construct your model. So your learnable parameters are the linear layers, the weights of the linear layers. So a natural way to make this equivariant with respect to a group action is by replacing the linear layers with linear equivariant functions, and then make sure that the activation function that you use doesn't break the symmetry, which in the case of graph neural networks, it's very simple because the action by permutations it would be commuting with any pointwise activation function, but then if we have other groups, it's not so obvious. One issue that this model has is that if I restrict the linear layers just to be linear equivariant, I may reduce the size of the space of functions significantly, and I may not get something that is expressive enough to learn functions that are useful for the problem that I want to solve. So sometimes we don't have that many linear equivariant functions or invariant functions. And so that is solved by going in tensor space. So basically, instead of looking at linear equivariant function that go from like your input RD to RD, you tensorize your input, and then you look at tensors of Ki tensors of your input, and then your output is also in a tensor space. And the way you think about it is like your group acts on a tensor as acting in each of the orders of the tensor, and then tensorizing that. So that's the extension of the group action to these tensors, the natural diagonal extension to the action. And so the question is, well, now we can make this class of functions more expressive, and going into tensors basically is considering, instead of looking at the linear equivariant functions, is looking at the polynomials, polynomial equivariant functions where the degree of the polynomial is the order of the tensor. And then the way we parameterize these linear equivariant functions is by using representation theory. So the idea is that we can decompose these tensor spaces in the irreducible representations using the Clebsch-Gordan decomposition, and then use Schur's lemma to write what are the equivariant functions here. And this is technically a little bit complicated to implement, but this has been implemented for SO3 in different papers, Fuchs et al. And Thomas et al. And there's a software package by Tesmith, E3NN that implements these models for SO3, and these are widely used in molecular dynamics, for instance, because that's the group action that is relevant in molecular dynamics applications. And so basically the idea is that you extend you have the original P4 neural network, you extend the linear layers to be on tensors now, and then for each tensor space, you decompose these using the Clebsch-Gordan coefficient in the irreducible representations. And now that you have the input space and the output space decomposed in irreducible representations, then you can see that Schur's lemma tells you that an equivariant map between two irreducible representations over C is either is a multiple of the identity or zero. And so you see which representations here and here are repeated. And then you have like one trainable parameter for each of these irreducible representations that match. And then you have to see how to go from C to R, but that's not very complicated. And there's a proof that this approach is universal. It universally approximates all SO3 equivariant functions if you allow your order of your tensors in your architecture to be sufficiently large. But basically, this is the computational approach that uses irreducible representations for implementing equivariant functions. Okay. Any questions so far?
I think we're good.
Okay, great. A simpler approach, but that is not as general. Here in the previous approach, you could do it for any group, but this one, you can do it for groups that you know the invariant theory, and you can actually compute the invariance, which you can do for like simple E groups, but maybe other groups are, like for instance, finite groups would be more complicated, is to use the invariance. So for instance, take the example of the dynamical system that I had earlier. So you have these point clouds, and you want to learn an invariant function of this point cloud. These point clouds say that you have positions and velocities, and you want to learn the energy of this point cloud. This energy is going to be an OD invariant function. So if I apply an orthogonal transformation to each of the vectors that define this point cloud, the function doesn't change. And so the question is, how do you parameterize that? And so using classical invariant theory, we know that the first fundamental theorem of invariant theory tells me that a function that takes n vectors in Rd and outputs a scalar is OD invariant if and only if I can write it as a function of the inner products of the input vectors. These are the invariants, and then any function that is invariant can be written as a function of these invariants. So another way to say it is like, I can, like, if I have an invariant function, I can write this feature space, which is the n by n inner products, and any invariant function factors through this space. And this is for OD, but there are similar characterizations for other groups, like the Lorentz group, symplectic group, rotations, etc. So for instance, for the rotations, the invariants are not just the inner products, but also the subdeterminants of D by D submatrices of the matrices of vectors, just because the SOD are the OD so that the determinant is equal to 1. So the determinant shows up here. And for the Lorentz invariant functions, then instead of looking at the regular in the Euclidean inner product, one can replace this inner product by the Minkowski inner product, which is like if you have vectors with like a time component and a spatial component, is the product of the time components minus the inner product of the spatial components, for instance. And this is something that is used for particle physics and in special relativity. So now that we have the invariants, we can get the parameterization of the equivariant functions by going from the invariants to the equivariant functions. And I'll show you how you can do it, but before that, maybe I'll show you the result. So the idea is that say that you have this particle system, and now we want to learn an equivariant function. So for instance, say I want to learn the position of a certain particle after a certain amount of time, or maybe the center of mass. Or if I want to learn the position of all the particles, then I will need to learn n independent functions that are all of them equivariant with respect to OD. So say equivariant functions. So if H is an equivariant function, if I apply an orthogonal transformation to each of the inputs, and then the output is transformed in the same way. And then it's not too hard to show that a function that takes n vectors in Rd and outputs a vector in Rd is OD equivariant if and only if you can write it as a linear combination of your input vectors. These are the input vectors, where the coefficient functions are scalar invariance functions as before. So basically functions of the inner products. So basically that is the characterization of the OD equivariant functions. And the one way we can prove this is by using the following argument. So say that H goes from Rd to the n to Rd, which is equivariant. We're going to construct a function f that is going to go from Rd to the n times Rd to R. And this function is going to be invariant. And it's going to be defined as f of b1, bn, b star is equal to the inner product between h of b1, bn and b star. It's very easy to check that this function is invariant just because I'm acting by the orthogonal by the orthogonal group here and here. So the orthogonal group is self-dual, so that they cancel out, the multiplication cancels out. And so this is an invariant function. So using the first fundamental theorem for invariant function, we can say that this is actually a function of the pairwise inner products. So let's call this like Bi, Bj, Ij equals 1 to n. And also the inner products between these guys, these inputs and the B star. So let's call this Bs B star from s equals 1 to n. But this function over here as a function of B star is a linear function. So whatever function I have here as a function of B star needs to be a linear function. So these terms, or another way to think about it is like if I take a derivative with respect to B star of this function over here, I get something that does not depend on B star. So so whatever function is of here, these guys need to appear linearly. So then this is going to be equal to a sum from s equals 1 to n of whatever thing you want of the first inner products and a linear term depending on Bs and B star. And then if I take the derivative with respect to B star on this side, and I take the derivative with respect to B star on this side, this cancels out, and I get the result that I had earlier. So that is the argument that shows you how you can go from the invariant functions to the equivariant functions. And so using the characterization from classical invariant theory, you can get a parameterization for the equivariant functions that eventually you can use for machine learning. So what I did here was just an example of like how to do it in the case of OD, but this can be generalized and can be said in more generality. So there's a general theory that goes from the invariant functions to the equivariant functions. This has been studied in classical invariant theory many years ago, and there's some results attributed to Lagrange and then written in some articles by Schwartz in the 70s and 80s. That basically, the basic idea is that if I have knowledge of the invariant maps that go from B times the dual of W to R, then that gives me a knowledge of the equivariant maps that go from B to W. And this is why I call this element here B star, but I didn't think of the dual space because I was working with the orthogonal group, so I kind of like didn't have to think about it in that form. Basically, the construction is based on the fact that if I have a group that acts on a space and I have a group that acts on another space, then the group acts on the maps from the space B to W, and the equivariant functions from here to here are going to be invariant functions in the space of maps, and you can reconstruct the equivariant functions from the invariant functions from this fact. And there is an algorithm that you can use to get the equivariant maps from the invariants, like the polynomial invariants, using the construction, a generalization of the construction that I just showed you earlier. Basically, I would need to find the polynomial, the generators of the algebraic invariant functions of B times W star that are G invariant, and then using those generators that are polynomial generators of the algebra of invariant polynomials, and taking the ones that are degree 0 in the second entry and the ones that are degree 1 on the second entry, the same construction that I did before will give you a complete characterization. But in order to do this, I need to have the generator of the algebra of invariant polynomials, which is not always very easy to get. It is easy to get in the case where the invariants are known, but I'm going to show you later some examples where that's not the case. But before I go to that, I'm going to show you like a toy example of how we can apply these ideas. In this example, I have this double pendulum with springs, and this function, and basically what I want to learn is the trajectory of the masses after a certain amount of time. And so the data here are the position and the momentum of the masses, the red mass and the yellow mass. And this is a O2 equivariant function because if I do a rotation that fixes the y-axis, then the predictions rotate. But also, if I rotate the gravity with the masses, then you can think of it as an O3 equivariant function. But in order to do that, the gravity needs to be an input to the model. So that is kind of thinking that, well, this is kind of like a coordinate transformation, and the gravity and rotating the gravity is like a passive symmetry, like rotating the positions and the velocities with the gravity gives you like just a coordinate transformation of the model, and this is another symmetry that you can implement. And another symmetry that the system has, because it's a toy example, this is a Hamiltonian system, the kinetic energy plus the potential energy is conserved, and that comes with a time translation symmetry. So how do I write a machine learning model that can implement this symmetry? So In order to do that, we're going to use some technique called neural ODEs, which is something very nice, very beautiful theory that that basically what it does is like instead of trying to learn how I go from like time 1 or time 0 to time delta t in this dynamical system, just like input output, I'm just going to encode the physics of the problem in the mathematical model. So I'm going to say, well, this relationship comes from a differential equation, and I'm going to learn what differential equation made that change happen from data. And so this differential equation is going to be O3 equivariant, just because we know this is like a property of the physics. So what I do is I train a function f theta, which is the parameterization of the differential equation. And then from f theta, I use an ODE solver to integrate the dynamics according to f theta, and then I do the predictions that the dynamical system would give me, the ODE integrator would give me. I compare the predictions that the ODE integrator gives me with the training data, and then I take a gradient step with respect to the parameters that define the differential equation. That's what the neural ODE does. And that is a way to learn a dynamical system from data. And so in this case, this is an O3 equivariant model. So f theta is implemented using the scalar model that I just told you earlier. So it's going to be a linear combination of the input vectors v, which are these, with scalar invariant functions, which are learned from data. So these fb are learned from data. And the architecture of the model is this, and this is the architecture that imposes the O3 equivariance. So that's one way of doing it. Another way of doing it is by imposing the Hamiltonian symmetry as well. And so what we can use that, and this doesn't use it, just says if this is any differential equation, but we know that this system is Hamiltonian. So basically there exists a Hamiltonian, so that the system, you can take the derivative of the Hamiltonian with respect to the position, negative the derivative of the Hamiltonian with respect to the position is the derivative of the momentum with respect to time, and same for the derivative with respect to the momentum. And so basically it's just that the differential equation satisfies a very specific form, which is like it is a Hamiltonian, and then what you can do is use a very specific integrator, which is the symplectic integrator that gives you the prediction of the dynamics. And now the Hamiltonian is actually an O3 invariant function of the data. Then basically you can learn it as a function of the inner products, given the fundamental theorem of invariant theory. And you can do the same thing. You learn a Hamiltonian, you predict the dynamics using a symplectic integrator, and then you take a gradient step with respect to the parameters that define the Hamiltonian. And that is a way to learn this dynamical system. And then numerically, you can observe that the most amount of symmetries that you implement in your model, the smaller the error, and the better the predictions are. So for instance, this MLP implements no symmetries, and these are finite subgroups. Well, these two are finite subgroups of OD, of O3. This is SO2, O2, and this is the O3. And this line is the neural ODEs that doesn't implement the Hamiltonian symmetry, and this line is the Hamiltonian neural networks that implements the Hamiltonian symmetry. Another interesting thing that you can do is you can also implement units equivariant. I'm not going to go into the details of that in the interest of time, but I'm happy to answer questions if you are interested in the end. And then there's a natural question. It's like, okay, I show you here that in this numerical example, I show you that when you implement more symmetries, then your error is smaller. And is there a theorem that tells you that? And the answer is yes. And under different model assumptions or under different assumptions, you can prove that implementing the symmetries in these machine learning models reduces the error. And for example, a simpler way of thinking about it is like, okay, if your group is compact and you're sampling your data from a measure that is G invariant, then you can show that if your target is invariant, then if you take any regression and then you project the solution of your regression into the space of invariant functions, then the error, the difference between the risk of both estimators is actually greater than 0. And it's not something that you can actually write down in the case of compact groups. In the case of non-compact groups, it's more complicated, but yeah, this is from this paper in ICML 2021. But there's other models that you can write down, and you can see how much do you gain by imposing symmetries. And it is expected that you're doing a regression in a lower dimensional space, and so the error of your regressions will be smaller. Okay, this example that I just showed you was toy example and this pendulum, but these ideas can be applied to more interesting or more applicable models. So, for instance, in self-supervised learning, what one wants to do is wants to learn a representation of objects in an embedding space. And these objects here are images, but they could also be images and text, or they could just be text. And basically the idea is that in self-supervised learning, the learning is based on augmentations. So here, say we have this cat, and we have an augmentation that takes this cat and makes it more yellow, or you have an augmentation that makes it more blurry, or does some shifting or jittering. And then what you want to learn is an embedding that takes images or data and gives you a representation in like, or here I'm overloading the word representation, but it's just like an embedding of your data into, say, the sphere. And typically in the classical representation learning literature, so for instance, in the simpler paper, what you do is you learn something that is invariant with respect to these augmentations, because you're thinking, okay, a cat is a cat. If you make it more yellow, then the cat doesn't change, like the concept doesn't change. And then you can do it with like paired images and text. So then you can learn a representation, an embedding that puts the cat in this point and then puts the word cat in this point as well. And you can use that for generative models. So say, well, I want to learn, I want to be able to generate things in this area. Like if I generate images that come from points in this area, they are all going to look like cats. And if I generate images that come from like this area of embedding space, they're all going to look like dogs. And the contrasted part is like asking that objects that come from different classes are embedded far away in the embedding space. And there's these info and CE laws that basically ask for that. Positive pairs get close, is invariant with respect to augmentations, and negative pairs get far away. And so what we can do is we can use these ideas from invariant theory to make this learned representation to be equivariant with respect to augmentations instead of invariant. So what I want to do is I want that applying an augmentation in the image space corresponds to applying a small rotation or orthogonal transformation in the embedding space, so that I get some form of interpretability in the embedding space. So I'm able to say, I know in what direction I should move in the embedding space in order to produce a dog that is more yellow, say. So what I want is that f of an augmented data point is a known transformation of the embedding of x. And this is something that mathematically cannot be done exactly because the space of augmentations do not form a group, but it's something that you could do approximately. Okay. So using the ideas from before, we know that if you have if you have this pair of points and this pair of points, then the inner product is preserved if and only if there exists an orthogonal transformation that sends this point to this point and that point to that point. So you can write an equivariant contrastive learning function by asking that the inner product of the embeddings of the augmented points corresponds to it's the same as the inner product of the embeddings of the original points. And if that's the case, then you can show that there exists an orthogonal transformation so that that makes the diagram commute. And then what you can do is you can modify the original Sinclair representation learning procedure and adding a loss term that asks for this embedding to be equivariant or approximately equivariant. And then if you can make that this loss term is actually equal to 0, then you can prove that it's equivariant. But in practice, it's going to be not exactly equal to 0, but it's going to be pretty small. And then you have some form of like approximate equivariance as well. But this is not constructive. So we don't know, we can compute it after the fact, but a priori we have no control of which augmentations correspond to which orthogonal transformations. But we know that whatever part of the group you don't kill when you send the augmentation to the corresponding orthogonal transformation, that would give you something that is close to a group homomorphism. So the group of augmentations that you don't kill is going to be approximately a subgroup of an OD. And I think that the mathematical analysis of these kind of methods is very it hasn't been done yet. So there's a lot of things to think about in this space. And so here this numerical example shows you that actually the orthogonal transformation that you learn is non-trivial, because say if this is your input and your query is a more yellow version of your original figure, then when you do a nearest neighbors in the learned representation space, you get something that captures the color shifting, whereas in the original Sinclair that was invariant with respect to this color shifting does not see that. So you can see that this is learning a non-trivial orthogonal transformation. Any questions so far?
I think we're good.
Great. So finally, I'm going to discuss, I'm going to go back to the point clouds example, and I'm going to tell you just in 10 minutes, how we can use Galois theory to implement machine learning models on point clouds. And so the idea is motivated by a problem in cosmology that basically starts with like you have a regression between point clouds. Some point clouds were generated by a cheap simulation that does just a dark matter only simulation of the a cosmological simulation that is only based on gravity. And there's another simulation that is more expensive that includes other things like electromagnetism and gas, etc. And so basically what Kay Story Fisher wanted to do in her PhD thesis was to be able to predict the properties of galaxies when you do a expensive simulation, but just from the cheap simulation that she had. So this, you can think of it as like an invariant regression on point clouds. And so these point clouds are, you can see them in terms of like you can see the modulo permutations because all the points are exchangeable, and you can see the modulo OD because the orientation of the points is relevant, and also ED, which includes translations, because also the translation of the simulation doesn't give you much. And this you can see it in the general framework of machine learning on point clouds. There's a lot of recent papers in this space with applications to chemistry, astronomy, computer vision, etc. So the setting is the following. We have in a point cloud, you can think of it as like in RD times n, where D is the dimension of the space. So here in this cosmology simulation, D is equal to 3. And n is the number of points, which here it can be huge. It can be like 10 to the 9, the number of points that you have in these cosmology simulations. And basically what we want to learn is a function that is EV invariant, so translation, rotation, and reflection, and also permutation invariant. So how do we deal with that? So in order to deal with translations, what we do, the simplest thing to do is just to take your point cloud and subtract the center of mass. This is the same as like choosing one representative per orbit of your translation action. And this in the machine learning literature is known as canonicalization, just like you learn your function in one representative of your orbit. And that you can do, you can do very easily for some groups. Then the next thing that we want to deal with is the OD action. And we saw the first fundamental theorem of invariant theory tells you that you can work with the inner products, and that gives you the OD invariance. So the next thing that we want to deal with is permutations. And so basically you have your point clouds, and you are acting by OD on the left and by SN on the right. And we know from the fundamental theorem of invariant functions, invariant theory, that tells you that the action of OD can be dealt with by working with the gram matrix of your data points. And now that you're acting by permutations, the action by permutations on the right corresponds to the action of permutations by conjugation on the matrix of inner products. And this action that I have here is the action that I showed you at the beginning that occurred with the graph neural networks. So you can use graph neural networks. So basically, this tells you, well, we can construct the matrix of inner products and then use graph neural networks, and that would give me a solution. We're not going to use graph neural networks because graph neural networks have a problem with expressivity, and maybe Melanie and Ron will talk about that tomorrow. I don't know. And also, what we're going to do in the end is going to reduce this complexity that graph neural networks have from O of n squared, which is like constructing the graph requires you to write O of n squared features, or like on O of n squared adjacency matrix, which we don't want to do because in this cosmology problem, our data was like n times d, where n was significantly larger than d. So I'm gonna show you how we use Galois theory, and then how we do a trick to reduce the O of n squared to O of n d. But I'm gonna give like the idea very quickly in the interest of time. But the idea is the following. So we have the group of permutations acting by conjugation on symmetric matrices, and this group is a subgroup of the group that just sends the diagonal elements to diagonal elements and off diagonal elements to off diagonal elements. You can see that if you act by conjugation, then you actually have to do this, but not every action that does this actually is an action by conjugation. They have to match. And so the inclusion of the subgroups is dual to the inclusion of the invariant functions. So if a function is invariant with respect to the large group, then it's also invariant with respect to the smaller group. And so we can characterize easily what are the functions that are invariant with respect to just this very simple action that decouples the diagonal of diagonal actions, which using the symmetric polynomials can be done very easily. And then what we're going to do is we're going to use Galois theory. And in order to do that, what we're going to say is that if we can construct a set of invariants that are only fixed by the desired group, like inside the bigger group, then those invariants generate the field of invariant functions. So basically, we're going to construct an invariant that is only fixed by the smaller group inside the larger group. And then this result by Rosenlicht in the 50s tells you that if you can use, if you get the field generators, then those field generators are going to be able to uniquely identify points, orbits, except for a small bad set, which is like an algebraic set that has measure 0 and is invariant. So we can use these field generators that we construct using Galois theory to separate almost all the orbits, and we're going to use those as features for our machine learning model. So basically, what we do is we say, well, we have the identity group is inside the group of permutations acting by conjugation inside this like group of permutations of diagonals and off diagonals, and so this inclusion of groups is dual to the inclusion of fields. So here we have the field of invariant functions permuting diagonals to diagonals and off diagonals to off diagonals, and here we have the big field, which is just the rational functions of symmetric matrices. And so we're trying to find generators for the field of invariant functions by conjugation, the invariant functions by conjugation. And so what we see is that this is very easy to characterize, and this extension, this field extension is Galois. So if we can find some F star generators that are only fixed by this group, then this will give us generators for the field of invariant functions that we want. And then we can check that what we need to add, the polynomials that we need to add, are these polynomials that are written as the sum of the xii's, so the diagonal elements, times the xij's of diagonal elements that share this I with these diagonals. And so this is the element that ties together the action of the diagonal to diagonal and off diagonal to off diagonal. So these polynomials are the ones that tie these two actions together. And basically you can use these scalars to generate the field of invariant functions by conjugation. And these are just the symmetric polynomials, the standard symmetric polynomials for the diagonal elements and the off diagonal elements. Okay. So in practice, we are going to use something called deep sets, which is a machine learning architecture that deals with functions from sets. We're not going to use the symmetric polynomials because many reasons, but one of the reasons that we want to use deep sets is because the way these deep sets are defined allow you to evaluate functions on pointless of different sizes, and that turns out that it's very useful, whereas the symmetric polynomials do not. And basically, the deep sets, you can look at this. This is a very well-known paper in machine learning that basically defines the functions on sets as this is like a function of each of the elements of the set. This is typically implemented with an MLP, and then you sum over all the elements in the set, and then you apply another function outside, and you can show that this model can universally approximate invariant functions in symmetric matrices outside this facet, which is invariant closing zero measure. And there's another trick that you can use to reduce this of n squared to nd complexity. And basically the idea is that if you have your point clouds, then what you can do is you can consider this point cloud over here. When you construct a matrix of inner products, it's actually like a rank D matrix. So you can use the fact that you can recover a rank D matrix from D rows or columns of the matrix. In this case, it's symmetric. And so basically what you can do is say, well, I take my point cloud, I construct an OD equivariant set of points in the end that is Sn invariant, and then I construct a matrix of inner products of these, and I take the rows of this matrix, and then I write a machine learning model based on these D rows, and then I can do the learning from here, and then this will allow me to reconstruct the entire set of inner products that I had earlier. I didn't explain this right, but I'm happy to discuss it later. But basically, this is a trick that doesn't really use the Galois theory thing that we used before to write an invariant function on that uses of and the invariant features instead of n squared. And the same, you can implement it using deep sets, and you have a similar result that you can universally approximate functions on point clouds outside this band set. Okay, so I'm not going to show you the numerical experiment for this, just in the interest of time. I'm going to tell you that the invariant, we can construct these invariant functions from point clouds via these lightweight invariant features using Galois theory. You can get genetic universality, and you can use tricks from low rank matrix completion and deep sets to get something that is information theoretically optimal complexity. And I'm interested in other applications of these. I'm more generally interested in use of symmetries and mathematical tools in the design of machine learning models with applications to physics and to engineering. And the tools that we use are invariant theory, representation theory, Galois theory. And I'm very happy to talk to you about this. I'm sorry, I cannot be there in person. Thank you.
Is there any